So here's a great question. Why are nuclides radioactive? Why do they undergo different types of decay? Well, the nucleus is a collection of nucleons, and that's the word to collectively refer to protons and neutrons because those are the significant particles in the nucleus. And those are held together by what's known as the strong force. Not a very fancy name, but that's what it's called, the strong force. And that's a fundamental force of physics. It only acts at really, really short distances. So you may have wondered at some point, how do all these positively charged protons stay together inside the nucleus, right? Because like charges repel, they should, fly away from each other. So there is that repulsive force between the protons because of their like charges, but then there's also the attractive, strong force between all of the nucleons. So that's the protons and the neutrons. So neutrons play a very important role in stabilizing the nucleus because they attract other nucleons without contributing to the repulsive force. So they make things more stable. The nucleons actually occupy energy levels as well. The good news is we're not going into that. The electron energy levels were hard enough. But there's a balancing point where energy payback from the strong force no longer compensates for the high energy state that added neutrons have to occupy. So it's not like you can just keep adding neutrons and it becomes more and more stable. So predicting which elements are going to, or which nuclides are radioactive, or what type of radioactivity they're going to undergo is not an exact science. It's kind of we've got some guidelines. And one of the things that's important to look at is the ratio of neutrons to protons. So N to Z. The neutrons stabilize the nucleus, right? And the protons contribute both attractive and repulsive forces. So this is a graph of the number of neutrons versus the number of protons. And so the slope here, N over Z equals 1, it would be along this line, right? And so we see here are all of the yellow nuclei. The green dots represent stable nuclei. So yellow is all of them, and the stable ones are the green ones. So we see there's a pattern here. Down here, the ratio is close to 1, and as we get higher and higher in number of protons, the ratio increases to be significantly above 1. And this is called the valley of stability because you can imagine that on this side is like a mountain, and on this side is like a mountain, right? It's like, well, if I go too far this way or too far that way, I'm going up in potential energy. And so this is the lowest, most stable place. It's called the valley of stability. You definitely do not memorize a graph like that. Students are always asking me, should I memorize that? No. They never say, should I memorize the symbol for chromium? Yes, you should. They're hung up on the wrong kind of things. Do we need to memorize the vapor pressure of water at various temperatures? No. But they can't remember the ideal gas law, right? I'm sorry. It wasn't a great day in 1A yesterday. We did the first practice for the lab practical. And one student actually asked me if the permanganate solution was made from pomegranates. It was not a joke. It's not a joke. He had a hard time saying permanganate, too. Actually, he had a hard time saying pomegranate, but I knew what he meant. Okay, sorry. I digressed significantly. So the type of radioactivity is going to depend in part on the N to Z ratio, because some forms of radiation cause the number of neutrons to increase or decrease, some cause the protons to increase or decrease, and that affects the N to Z ratio. And so we can see that if a change in the number of protons or neutrons causes that ratio to become closer to the stable ratio, that's probably what's going to happen. So if we've got our N to Z ratio too high, that means there's more neutrons than ideal. So too many neutrons, and so those will tend to convert neutrons to protons and do the beta decay. If N to Z is too low, that means the nuclides have too many protons. So then they will tend to convert protons to neutrons via positron emission or by electron capture. Alpha decay also raises the N to Z ratio, but the effect is not as great, so it's not as significant. So there's two methods for predicting the type of radioactivity. One is to look at that table. It's actually figure 21.5. The other is to compare the mass number of the nuclide that you're looking at to the atomic mass on the periodic table. So the atomic mass is an average of stable nuclides for that element, right? So that's going to represent an N to Z ratio that's about right for that given element. So if we look at ruthenium, where'd you go? There it is, number 44. So ruthenium's element 44, ruthenium 112. Let's see here. Ruthenium 112, so 112 minus 44, shoot on the calculator, is 68. So 68 protons to 44 neutrons is about 1.5. Right? So that's high. When we look at the average atomic mass for ruthenium, it's 101. So that tells me that a stable nucleus probably has a mass number of 101, right? So if it was 101 minus 44 is 57. So 57 over 44 is 1.3. So here I calculated out the number of neutrons and the ratios, but you can actually look at, just compare this mass number of 112 to the average atomic mass of 101. These are all ruthenium atoms. They all have the same number of protons. So that tells me, because this mass is higher, it has a lot more neutrons than the average stable ruthenium atom, right? So then we would predict that it would undergo beta decay, which will reduce the number of neutrons. Any questions? So predict whether each nuclide is more likely to decay via beta decay or positron emission. So let's review real quick here. So here's positron emission. In positron emission, a proton becomes a neutron, right? So that's going to increase the number of neutrons. So if our mass number is lower than the average stable one, then we're going to look for positron emission. Beta decay causes us to lose a neutron and gain a proton. And so that will decrease the ratio. That make sense? You guys are all just kind of dead tonight. You're all stressed out about the lab practical, aren't you? Some people are, yeah. Others of you, I guess, are so stressed you can't even speak or nod your heads. Okay, so lead 192. We're going to look at lead on the periodic table and see that the average mass is 207. So this one has a mass number of 192. Does it have too many neutrons or not enough neutrons? Not enough. Low in neutrons. Right, so then we need to increase the number of neutrons. So how are we going to do that? Positron emission. Okay, so PB212, again, we're comparing this to the average atomic mass for lead, which is 207. So this one has more neutrons than average, right? So we need something that's going to reduce the number of neutrons, which would be the other choice, right? Beta decay. You get the idea? So xenon 114, look at the average atomic mass. I looked at it and I forgot it already. 131. Does this have too many neutrons or not enough? Not enough neutrons. So what's it probably going to do? Positron, yeah. There will likely be a question similar to this on an exam. This is not something that I just remember like 2 + 2 is 4. I have to think it through every single time, because how often do you do this, right? Lately it's been once every 3 years, so not so often. But you just want to look at the average mass, compare it to this mass number, and then look at the different types of radiation. You should memorize those particles and what's happening, and so then you can look at what's going on and see, oh, well, that's causing the mass number to go down, or that's causing the mass number to go up, right? And you can just sort of reason it out. There are also what are called magic numbers. So it's not just the ratio, it's also the actual number of protons and neutrons that affects the nucleus. And this is just, people observing patterns. So there's a large number of stable nuclides that have an even number of protons and an even number of neutrons. There are only 5 stable ones that have odd protons, odd neutrons. Oops. So we see the majority of them are even. And these guys here, we've got an odd even and an odd even. So the reason for this is that nucleons also tend to pair together not just like, but sort of like electrons do, right? And so the electrons had spin, and they spin paired, and then they were able to hang out together. So similar sort of thing happens here. So we have learned that atoms with certain numbers of electrons are uniquely stable, right? Noble gases, because their valence shell is full, right? Has to do with the different levels that the electrons occupy. So similar thing happens with the nucleons. And so if N or Z, so number of neutrons or the number of protons, is 2, 8, 20, 28, 50, or 82, those guys are really stable. Do not memorize those numbers. They're not that important. And another really good one is 126. And notice that all of those are even. It's one of those, oh, look at that. What does that mean? Not so sure. Atoms with an atomic number greater than 83 are all radioactive. They will decay in one or more steps. And so if you look at the periodic table and you look at the average masses, right, we get up to bismuth at 208.980, and then after that, all of them are whole numbers in parentheses, right? 209, 210, 222, because all of the nuclides are unstable, and so you can't get a good average atomic mass. So mostly what will happen is alpha and beta decay, because that's going to get the nucleus smaller, right? It's got too many protons, also has too many neutrons. We've got to get down to Z being 83 or less in order for it to be stable. So alpha emission gives us, we lose 2 protons and 2 neutrons, right? So that's kind of nice. And then beta decay, we're losing neutrons. We're losing protons and gaining neutrons. There may be gamma decay also, but that just gets rid of excess energy. Yes?
When you're pointing out the atomic masses for the radioactive elements, up there, thorium, protactinium, and uranium have more precise.
You're right, they do.
Is that because they're more stable in nature than the other elements there? I know that there's large deposits of thorium and uranium in the Earth.
That's an excellent question. We should look that up. We should look that up. So that was a good question. So this is an example of a decay series. So uranium-238 will decay through a number of steps. And sometimes there's different options for it. And it's going to keep going until it ends up being lead-206. And some of these cause the protons to increase. Many of them cause protons to decrease. All of them are causing the neutrons to decrease. Any questions?